good. Thank you for the introduction. So welcome to this talk on enhancing CTI processes with code search technology. Carlos, my colleague, is getting mic'd up. He's a threat analyst at Threatray, and myself, I'm Jonas. I'm the CTO and co-founder of Threatray. And what we're going to talk about is mostly what kind of impact search has in cyber defense. And we already have search capabilities, and what we're going to explore a bit is what if we could also search through binary code. And this is then something we can apply to different use cases, and we'll show two use cases here, one of them being malware identification, and the other being making OSINT searchable. So search is quite prominent. That's why tools like Splunk or Elastic exist. So, for example, if you have some sort of malicious URL pattern, you can easily use those tools to check if any of my hosts in my infrastructure have connected to any URLs matching this kind of pattern. And without these search technologies, this would be a very hard thing to do. So what if we could do the same for binary code as well? So if you have some sort of a new malware binary, you want to know, have I seen anyone in my organization having, for example, executed a similar binary? And that's something that is not really well solved nowadays. And in this talk, we'll explore if we had these capabilities, what kind of benefits, what kind of merits could we draw from that? So before I talk about some concrete applications and use cases of these capabilities, let me give you a little bit of an impression of what it means to have searchable binary code. And to have search, you always need to have some sort of a sense of similarity between two entities, like two URLs, right? In this case, what is similarity between two entities of binary code? And there's multiple approaches you could take here. For example, you could use a tool like SSDeep, which generates a fuzzy hash over the content of a file. And then if two fuzzy hashes are similar, then you can say, well, the content of those binaries is similar as well. That's quite a broad way to look at similarity because it includes metadata, headers, strings, as well as code. Another approach would be to extract some byte sequences from the code of this binary and then start to compare byte sequences with each other. And that gives you a rough estimate of similarity as well. But that's quite brittle to compiler differences or to mutations and variations. A much better approach that we already have nowadays is tools like BinDiff or DFRWS. And these tools essentially compare two binaries by looking at structural similarities between the functions of those binaries. So if you find a lot of structural similarities on those binaries' functions, you could then say that these binaries are similar. And this is a very good and well-established way of looking at code similarity. The drawback in this case here is these are tailored for one-to-one comparisons. So you have two binaries that you can compare. And to build search, you need to compare one binary to a million of binaries, right? So what we need to have is BinDiff at scale, essentially. And there's ways to build a BinDiff at scale. We're not going to explain how that works, but we just assume we have capabilities to do BinDiff at scale. So if you have that, then you can build your binary code search engine. And here we have this binary A, and we want to have a list of similar binaries from our search engine. So what we need to do is we decompose it into its functions. We index the functions in some sort of database, and then our search engine can tell us, okay, there's a list of similar binaries, and they are similar because, in this case, binary B has 290 out of 350 functions that are similar to the functions in binary A. And with this, you have a very rudimentary approach of finding similar code. Now, this is something we've built at Threatray, and we use it on a daily basis for a variety of use cases. And one use case that is very interesting and pops up all the time is malware identification. And malware identification is about determining the malware family for an unknown piece of malware. And that's quite an important step in any CTI process, because if you can identify what you're dealing with, you're already many steps ahead in terms of trying to resolve a specific case, for example. And now, why is search even interesting in the area of malware identification, you may ask? And what we're trying to do is we look at malware identification through a bit of a different lens, and we try to model the problem of malware identification as a search problem. So, for example, if you have some sort of an unknown binary and you can relate that unknown binary to a confirmed Cobalt Strike binary, you could derive that, okay, this unknown binary is likely also Cobalt Strike because they're similar, right? Now, that's the idea behind it, and in reality, it could look like this. So if you have some sort of DLL in this case, you could start to identify that as, in this case here, vSingle, which is a malware family from a North Korean actor. And we can say this is vSingle because 80% of the code in this DLL is actually code we've seen before from confirmed cases of vSingle. So now again, you could ask, well, why is code search so interesting? I couldn't just use BinDiff, for example, and or YARA rules, if you like. You get resilience against malware variants with code search technologies, and I'll explain why in a bit, but let me give a little bit of context why it is interesting to have resilience against malware variants. And the reason being is that a lot of new malware is essentially a variation of previous malware that has been seen before. And if we look at VT, for example, the statistics say that they have around 1 million plus minus new malicious binaries every day. And these variations happen for two particular reasons, and one of them is to bypass detection. That's a very explicit way to create a variation. And the second is an implicit variation, which is malware evolves, just like software. And of course, there's truly new malware which hasn't been seen before, but that's a pretty rare case overall. So what this leads to is that you need to have some sort of solid signature approach for malware families that is resilient against those kind of variations. And now, this is what makes code search so interesting, and I will briefly explain why you get resilience against these variations by using code search technologies. So let's make an example here. Say you want to identify a particular malware family, and now you have 4 variations of this malware family that you know of, and these variations, they contain certain pieces of code, for example, for networking, for crypto, and so on. And this code has changed over the years a bit. And now we define our signature essentially as all of the code in all of these variants we take, lump together in one big pot, so to speak, and that's our signature. Now the signature contains hundreds or thousands of code functions from all of those different variations and functionalities. And now if a new variant comes along, we can relate this new variant to part of these previous variants. So in this case, this new variant maybe changed persistence or some utility functions, but we don't really care. We still get a good match because a large part of this variant we have seen before. So essentially now what we did is we bin-diffed, right? We bin-diffed this new variant against a couple of older variants. And code search is interesting here because you can do this not for one malware family, but for hundreds or thousands of malware families, which makes this actually relevant. So you can do that at scale. And that then gives you capabilities that allow you to very easily actually create solid signatures based on these code search technologies. So in the next part, Carlos will now showcase exactly on how these mutations can happen and why such technologies is resilient against that.
Okay, thank you, Jonas. So now you remember Jonas talked about most of the malware activity is performed by mutation or variation of the same malware families. That is very important because that is where code search and code identification is so important. For example, in this case, we are going to take Mimikatz. That is a very well-known tool. It's a credential dumper. And we are going to modify Mimikatz until be able to bypass Windows Defender and some Java rules. For example, here we're going to use Defender check in order to know where the antivirus signature is matching. This is an iterative process. Then we have to go to the project, modify again, and then we're going to do the same with the Java rules. In this case, we have picked the following ones from public source. And then we're going to use MetaMe, that is a metamorphic engine that allows us to replace some instructions for equivalent ones. For example, a sort instruction could be replaced by the sub operation or instruction. A move operation could be replaced by a push and pop. So and that is automatic. So now I'm going to show you a video. Let's see. In this case, we are going to start. Imagine we download the GitHub, the project from Mimikatz. We compile the sample. We have the sample there. We run Defender check. And we're going to see how Defender check is detecting the sample, because at the end, Defender check shows the detection from Windows Defender. So now we will have to go to the project, modify the strings or the code, and do again. Now we are going to turn on the antivirus, and we're going to see how it's detected. Okay, this is a pretty simple test. Then the same with the Java rules. In this case, we have those Java rules. Part of them there are strings, other parts are from specific patterns that Mimikatz need in order to detect some APIs. And as we can see there, when we run the check, there are a lot of matches there. So it's detected. No, we can say that Mimikatz is detected with those Java rules. Now we are going to submit the Mimikatz sample to the platform in order to use code identification. Now we can see that it's analyzing in static. Then we're going to see the results, and maybe 50% of the sample is Mimikatz. The other part is more like common libraries or functions that are not only related to Mimikatz. So it's detected. Now we are going to try to bypass the antivirus. We have modified several strings. We have changed some structure from the binary. We have changed the icon, etc., a lot of stuff. And now we are able to bypass the antivirus. With Defender check, there is no detection. We can execute without any problem Mimikatz. We can run some commands. In this case, this is a virtual machine, and the password is infected, so don't worry, I don't have any problem with that. So NTL hash. Then it's running down. Then we're going to try to run against this modified Mimikatz against the Java rules. We're going to see, okay, there are not detection here because we modify strings and other stuff. We're going to add another layer. We're going to use MetaMe in order to replace some instruction by others that are equivalent. This is automatic. This is very easy to do. You can download the project and execute. You don't have to do anything. And now we're going to see what's happened against code identification, both versions, the Mimikatz modified and the Mimikatz modified plus the MetaMe modifications. And we're going to see what are the results here. We are analyzing in static. Remember, for example, this one is the first one, the modified, and the result is exactly the same, or we can say that is mostly the same. And the other one is pretty similar. So what is happening here? Sorry. Okay. What is happening here? We have modified strings. We have modified some specific functions from the modified Mimikatz. but we are able to detect almost in the same way. Why? Because we don't care about strings when we have to do code. When we do the code signatures or identification, is not important, the strings. We have, for example, in this example, there are some functions that match perfectly. There are other functions that has been modified enough, so now we are not going to be able to detect in the same way. But the ones that has been slightly modified or modified in some specific way without modifying the workflow or the function or too much, at the end we are able to continue identifying it as the same function. So that is very relevant because performing hard modification into the binaries is complex if you don't have the source code. And sometimes if you want to modify a lot, this kind, for example, from malware as a service is something that is not usual to have the source code, or maybe you don't have the source code, you only have maybe another layer that is the packer. So the signature will work well against the sample. And another thing is that if you want to modify enough the binary, imagine that you are adding control flow flattening or whatever, at the end you are making more difficult to debug. So at the end, we can say that adding code identification adds another layer and makes more difficult or more difficult to bypass and is more resilient against change. And now Jonas is going to continue.
Thank you. Okay, so now let's talk about a second use case, which is quite interesting, and it's about making OSINT searchable. So, wrong way. The problem is quite simple. Right? If you have some sort of unknown binary file, you want to know, is this binary file somehow related to any OSINT source? And OSINT source could be a tweet, a report, a block, and so on. And there's multiple ways to approach this problem. On one hand, you could just simply calculate the hash over this binary and then search if any of those sources contain this hash. And that might be a bit problematic, or you have to be very lucky. As we've seen, there's so many variations of malware, and it's so easy to create a new variation that's pretty unlikely that you'll find good matches here. A bit of a better approach is to throw it into a sandbox, extract some behavioral artifacts like IPs, mutexes, URLs, and try to find if any of those artifacts in an exact or fuzzy form appear in those reports. That's already better, right? Or you could take an additional step and say, I'm going to use Yara or these code search technologies. I try to identify the malware family, and if I can do that, then I can at least narrow down a bit the amount or the scope of reports to look at. So assuming all of this fails and you don't get any good matches here, we could now add an additional layer by using these code search technologies. And what we're doing here is we take this unknown binary, we ask our search engine, have you seen this binary before? And the binaries that you've seen before, are they somehow mentioned directly in any of those OSINT reports? So with that, now we essentially can turn binaries into searchable IOCs, right? That's quite a powerful approach for solving this problem or trying to solve this problem. And Carlos will also now explain on a concrete example of how this can be applied.
Yes, thank you, Jonas. We had an incident response case where we received a memory dump, but the problem, we were able to extract some artifacts, but this binary was completely broken, so were unable to detonate it properly, to execute it properly. So, and with the information that we had in that moment, we were not able to find anything relevant or interesting. So we thought, okay, we are going to use our search capabilities and link with the OSINT information that we have in order to see what's happened or if we are able to relate to something. So we submit the unknown binary. We found some matches. In this case, one of them that is related to the Japanese threat. We have a match with a sample almost 51%, and another with a semantic report that they talk about B-single2, about Lazarus, etc., actor, etc. So only in a matter of seconds, we were able to relate an unknown binary without having previous information directly with a malware family, without needing to have any signature, anything previously. We can link directly thanks to the code search capabilities. And then we can go to the report, see what they explain here about the threat, etc. We see communication, etc. But at the end, most of the IOCs that you can find in this kind of the reports, usually there are domains, URLs, and hashes. But currently, we don't have very good ways to look through binaries, no? That at the end, the hash is the representation of those binaries. That is not easy. At the end, there is something that we can find always in the report, but who cares? If you are not going to do more research, maybe you add to your list of malicious hashes, and that's all. But if we check the semantic report, it's similar. We have some TTPs here about the different states. They talk about, okay, the malware in a specific stage create a named pipe called pipe, okay? It's not too much. But at the end, what we have here, lot of IOCs related to the binaries, the hashes, no, of those binaries. So the important here, and by my experience, doing research and etc., at the end, this last year, we don't have, or currently we don't have a good way to move through these binaries or to do similarity without having to download them, do all the manual effort. And with this code search technology, we are able to look for this binary directly. We can compare against the others. So it's pretty powerful and save a lot of time. But and maybe you don't need to be a reverse engineer to pick the sample, analyze properly, and do all the research. Maybe you can directly, from the CTI role position, you can, okay, I am expert in this kind of reports. I don't need to do this manual research because it's performed automatically by the code search system. And now Jonas is going to explain how this is possible.
So we omitted some key points here on how to make this possible, so I just want to go back a bit and explain what you need to have these kind of capabilities besides obviously a search engine. So of course you need to somehow find or acquire these reports from different sources. You need to parse them, extract the hashes, then you need to find or download the malware binaries as a next step, and then you can start to index those binaries and link the binaries with the specific OSINT sources, and then you can essentially display results of relevance in this area. So that doesn't sound super bad, but there's a couple of real-world challenges around making this OSINT searchable, but also to go back to the malware identification, which kind of goes in the same area. So what you very often have is obviously packing for malware binaries. So what you want to do is to unpack them beforehand, right? You either detonate them in some sort of sandbox, or you have some static unpacking, which gives you then, let's say, the pure binary or secondary stages of a binary. So that's quite necessary to have. Then what's also very important is, since every binary has some library code, you need to somewhat differentiate what is the user code and what is the library code. Because if you don't do that, you might end up comparing binaries and finding matches based on using the same libraries, which is not really something you want. So you need to be able to differentiate between those types of code. And then lastly, you need to have the actual binary, which is often the hardest part. Right? Not every binary in those reports or these sources is accessible or available. So this part only works if you actually can get the binary. Good. So what can we take away from all of this? And we've seen in the beginning that there's a large amount of variations on malware attacks, and that kind of necessitates have some sort of resilient identification capabilities. And we think that code search technology can provide an additional step towards this direction. Then, on top of that, we've seen that these OSINT reports are quite valuable, but a lot of its value is kind of locked behind hashes, which are not very suitable to use. And also here, we essentially showed that we can transform these hashes into searchable IOCs, essentially. And the idea behind that is to unlock more potential behind the reports. Good. That was all. Thank you very much for your attention. If you have more questions.
Thanks, Jonas and Carlos. We have time for questions. Do we have any question for the guys? Yep.
Yeah, so the question is, if you have a lot of these malware artifacts, can you scale? If I understood correctly, right? And yes, we can. We track 1,500 plus malware families, and the system we have scales to millions of binaries, and you can do essentially real-time searches. So yes, you can build technology that can do BinDef at scale.
We still have time for more questions about this capability that...
Okay, so the question was, how do you collect the malware and how big is the database? So we collect from various sources, either public sources or private sources. So it's a very good question, because unless you find binaries, you cannot do much, right? And there's obviously ways to find binaries. And the database is close to 100 million binaries, I would say. Not all of them are relevant for identification. So what we've seen in the beginning is that you ideally build some signatures, and this is only a very small subset of these 100 million binaries. Maybe, I don't know, a couple, 10,000 binaries are already sufficient to have very good identification. The huge mass of other binaries that we have is more contextual information. Right?
Any more questions, guys? We still have time for one question, if you want to. Yep.
So question is, how do you handle code obfuscation in the functions you extract? So that's a very good question. To give an honest answer, you could get around every type of technology by applying some type of obfuscation. So even this approach that we showed, if you do very heavy obfuscation on the code level, you could probably bypass this as well. Generally, we don't see it much. That's why we're not doing a lot against it. Having, let's say, a good decompiler gives you a very, let's say, resilient way to extract functional properties. And then essentially we work on top of these properties, which are somewhat resilient against these types of obfuscation. So from our experience, code level obfuscation is not such a problem. It's more unpacking that you have to do.
Thank you very much.
Thank you.
Thanks, Carlos and Jonas. It was a great presentation, and let's upload again and.